All right. Today we're going to focus on refraction calculations, right? Not too much on the theoretical part, just the calculation part. So let's get straight into it. Um, let's assume that we have an air glass boundary and we have light trying to move from the air part into the glass part. Now, anytime a wave, now it doesn't have to be light, but in this case it's light. Usually when a wave tries to go from one medium and tries to enter a different medium, the angle will change. Everything here on the side are formulas that will help us calculate the change in the angle. Right. So to do these questions, you are usually required to know something called the refractive index, whose symbol is N. Now, refractive index usually entails two materials, two mediums, right? No one is supposed to say the refractive index and just put an N and then give you a value. It's supposed to have two letters, one on either side. The two letters have a very important purpose. First of all, in this case here is air and glass, so the A obviously represents air and the G obviously represents the word glass. But you notice that the A, if you're reading it this way, the A comes before the G. That means the light was in the air part first and it's trying to go into the G, to the glass. So this refractive index value only works if it is going from air to glass. Okay, now that's very important, right? Suppose, I'm just saying suppose, and I'll continue with the calculations just now. Instead of the light going this way, notice the arrows are pointing this way. But let's just say the light were to go the other way. It were to reverse direction. In other words, it would start from the glass and try to go into the air. Would the refractive index still be 1.8? No. First of all, we will have to write that refractive index differently. If you are trying to go from glass to air, you have to put the G first, then the N, and then the A, because it's going from glass towards the air. And the refractive index will not be 1.8. Whenever you are trying to find the refractive index in the opposite direction, you have to flip the refractive index of the original one. So in other words, the refractive index from glass to air will be 1 divided by 1.8. Of course, you can reduce it to a decimal if you wish. 1 divided by 1.8, and this will give us 0.56. That is what basically this formula here is saying. A lot of people see this in a textbook and they don't really understand what the formula is trying to say. Alright, so that means if I had two different materials, let's call it A and C. Let's say something was going from A to C and the refractive index was 2/3. Right, so this time I gave you the refractive index as a fraction, not as a decimal. But let's say the light were to reverse direction. And instead of going from A to C, whatever A and C represents, if the light was going from C to A, you will need to flip this. Or if you want to throw it underneath a 1. But when you throw a fraction underneath a 1, it will flip. In other words, you will get 3 on 2. And 3 on 2 is the same thing as 1.5. So be very careful with refractive index, the values. The direction of the light plays a very important part, right? Alright, so don't worry, I'm going to be playing all the different types of tricks that the examiner can pull on you. So let's see. So the light is going from air to glass. Do we have the correct refractive index? Yes. A comes first and G comes second. This means the light is in the air first and afterwards it goes into G. So no tricks. So let's use this formula. This formula helps us to calculate the angle. Now this formula, be very careful. Notice that the A comes first. The angle A goes on top. So the angle in the first medium goes on top. And you notice the B comes second. So the second letter, the angle goes underneath. Now please don't venture more into this video. unless you went through the physics basics already. There's 3 videos I posted prior to this one, and I really don't want to get hung up on the mathematical aspect of it, where, because today when we're solving for a letter, we'll be cross multiplying and do the mathematical part kind of fast, because we already did it in a previous video. Alright, so let's go ahead and find the angle in glass here. Also, well, let's write down the formula. The 2 letters are A and G. A and G. It's no longer A and B, because the first one is A and the second one is glass. Sine of the angle in A. The first letter goes on top, and sine of the angle in glass. Alright, so let's plug in the values that we have here. Right? I'm just going to create a little border here, so we can work separately here. What is the refractive index from air to glass? Well, the refractive index from air to glass is 1.8. So I'm going to replace this with 1.8. Is equal to sine of the angle in air. What's the angle in air? 40 degrees. Divided by sine of the angle in glass, which is what we don't know and it's the aim of the question to find. So all we have to do is use our mathematical skills to find G. So 1.8 is the same thing as 1.8 on 1. Let's find the value of sine 40 on our calculator and round it off to 2 decimal places. It's regular sine, so you're just pressing sine 40 equal, and you will get 0.64. So that means this here is sine 40, the whole thing I can erase it and put 0.64. So let's cross multiply now, folks. Doesn't matter if we do this one first or this one first. Let's do this one first. Right. So 1.8 by sine G is 1.8 multiplied by sine G. We can't do anything there at the moment. Is equal to, and we cross multiply the other diagonal. 0.64 multiplied by 1 is 0.64. Remember, we're solving for G. So throw across the multiply and we will get a divide. Let's divide that on our calculator. 0.64 divided by 1.8. So sine G, when you divide this here, is 0.36. We are still not finished. Remember, we are trying to find G, which means we have to throw across sine. And when you throw something across, you get the opposite. So I'm going to move across here. When you throw across the sine, the G alone will be left on this side. And the opposite of sine is sine inverse, 0.36. So in my previous video, I showed you how to find sine inverse. You press second function, sine. You'll see the sine minus 1 up here, and just type in 0.36. And we get 21 degrees. Well, real close to 21 degrees. So the angle G is 21 degrees. So 21 point something. I'm just going to put 21. Right, so this is the answer the examiner is looking for. Now, there's a way to figure out that if you're on the right track, because in the exam, you don't have someone to ask on the spot if you are right or if you are wrong. But there's a way to figure out if you're on the right track at least. Anytime your refractive index is less than 1, the angle is supposed to increase. If the refractive index value is more than 1, the angle decreases. If the refractive index is exactly equal to 1, the angle is not supposed to change. So let's investigate to see. Remember, we're putting the answer here. Here's 21. Let's see if our answer could be correct. The refractive index from air to glass, and that is the direction the light is going, is 1.8. I believe 1.8 is bigger than 1. 1.8 is larger than 1. So the angle is supposed to decrease. You notice the angle in air was 40, and when it entered the glass, it changed to 21. 40 to 21 is a decrease. So at least I have some confidence in myself now that, hey, most likely I'm on the right track in the exam. Alright, going to do the second question now. Alright, question 2. here we have a light ray, right? Once again, it doesn't always have to be light for these formulas to apply, and that's using light. Let's say we have a red beam of light that is trying to go from water into oil. So it's going from water into oil. The angle in the water is x, the angle in the oil is 70. Alright, so let's see if we have the correct refractive index to this question. W then O. This means that in the question, the light should be going from water. It should be starting in water and ending in the oil. Yep, seems to be correct. It's starting in water, then it is going into the oil. So let's write the formula. WNO is sine of the angle in water. Remember, the first letter, the angle goes on top. And guess what will go on in it? The O. This is the O, not a zero, right? The O represents the oil. So let's write what we have here. Make a little barrier here. WNO. The examiner gave us 0.75. Sine of the angle in water. We do not know the angle in water. And the examiner, let's assume he drew the diagram first. And he's calling the angle in water X. And the angle in oil 70 degrees. So the aim of the question here obviously is to solve for X, right? So 0.75 is sitting as 0.751. I believe we can find sine 70 in our calculator. Sine 70. If we round it off properly, we get 0.94. So I can erase this sine 70, the whole thing, and put 0.94. All we have to do is cross multiply. I'm going to do this one first this time. Right? Sine x by 1 is just sine x. And if we multiply 0.75 by 0.94, we will get 0.705. Obviously, if you round this off to 2 decimal places, we get 0.71. So we want to solve for x. Throw across sine, and the opposite of sine is sine inverse. So we have to sine inverse 0.71. So that means x is what? Second function, sine 0.71. You will get 45.23 degrees. So this angle here, x, is roughly around 45 degrees. Right? So I just left only 2 decimal places. Is our answer correct? Well, let's go back to this little chart here. Our refractive index is 0.75. 0.75 is less than 1. That means the angle is supposed to increase. Remember, the light is going this way. So that means it started off in water at 45, and at the end of the question, it changed to 70. 45 is less than 70. The angle did increase. So most likely I did everything right. Alright, let's try another question. Alright, so welcome to the third question on refraction. So here we have a boundary. So instead of the light coming down, it's going across this time. Nothing is wrong with that. So the light starts off in diamond, and it's trying to enter into glass. Right? So, and the examiner gave us the refractive index to be 0.45. But there's a trick in this question. First of all, the refractive index goes from, according to what he gave us, from glass to diamond. Let's look at the actual scenario. Is the light going from glass to diamond? No, it's actually starting off in diamond and trying to go to glass. This is not the refractive index for the scenario. So by using this formula, we actually need the refractive index from diamond to glass, the opposite direction. So we need to take this refractive index and flip it or throw it underneath a 1. You can leave it like this, or you can simplify it on your calculator. I prefer to go with simplifying it on the calculator. 1 divided by 0.45 is roughly 2.22. So this is the actual refractive index we need for the question today. So don't fall for those simple tricks. Let's write down the formula. Remember, it's this one we're looking at. We don't care about this guy anymore, right? He was there to fool us. So the light is going from diamond to glass. DNG is equal to sine of the angle in diamond. First letter goes on top. Second letter goes underneath. Right. So let's write in what we have here. The refractive index from diamond to glass is no longer 0.45. It's actually 2.22, right? And this is equal to the sine of the angle in diamond. The angle in diamond is 60 degrees. Divided by sine of the angle in glass, which the examiner chose to call x. All we have to do is find sine 60 and cross multiply again. 2.22 is the same thing as 2.22 on 1. Let's find sine 60 quickly. Sine 60 is 0.87. So that means the sine 60, I no longer need him. So he is 0.87. Let's cross multiply. Doesn't matter which diagonal first. So here we get 2.22 multiplied by sine x. And anything multiplied by 1 is itself. So we're trying to solve for x. So throw this guy across first. His multiply becomes a divide. So when we divide it, we just get this divided by 2.22. So that means sine x is equal to 0.87 divided by 2.22. 0.39. But we are not finished. We are trying to solve for x. So now we have to throw across the sine. And remember, the opposite of sine is sine inverse. And who's waiting on this side? 0.39. So I'll put the answer over here. So x is equal to, find the sine inverse of 0.39. Second function, sine 0.39. And we get roughly 22.95 degrees. Close to 23 degrees. So that means this angle here is 23 degrees. Are we correct? Remember, the real refractive index for this scenario is not the 0.45, but rather the 2.22. It's going from diamond to glass. 2.22 is clearly bigger than 1. So the angle was supposed to decrease. Did it decrease? It started off in diamond at 60 and then it went to 23. 60 is bigger than 23. So most likely we are on the right track. Alright guys, next question. Alright, so welcome to my fourth question on refraction. Alright, so let me describe the scenario here. We have a tank of water and there's a fish inside here. They want a little light. I forgot the name of the fish. You can leave the name of the fish in the comments. It's the same fish that was in oh god, Finding Nemo. I can't remember the name of the fish. Anyway, the light from the fish comes from the water and then it goes into the air where there's a person eyeing the fish, right? Probably he's hungry or something. I don't know. But the examiner gave us the refractive index from air to water. E and W obviously represented air and water in that order. And he says the refractive index from air to water is 4 on 3. And he wants us to calculate the angle in the air part. Is the examiner trying to trick us? Yes. Because it's going from, the refractive index is from air to water. But this light starts off in the water and it's trying, well, it didn't try, it went to the air. So we actually need the refractive index from water to air, not air to water, right? So what is the refractive index from air to water? We need to flip this. If we flip this, if we throw it underneath a 1, right, we throw the whole thing underneath a 1 and we simplify it, we will just get 3 on 4, right? So the refractive index from water to air is 3 on 4. Right? So let's do the calculations from this point now. Right? This time I'm going to use the whole fraction and I'm not going to change it to a decimal. I know 3 over 4 is 0.75, but I've seen some students, they're so accustomed with fractions, so they leave it as a fraction. So let me do one question as a fraction for them. So WNA is equal to sine of the angle in water. First letter goes on top, second letter goes underneath. WNA is how much? WNA is 3/4. So I can erase this and put 3/4. What's the angle in water? 60 degrees. And of course, we are trying to find the angle in air. So let me use my calculator and figure out the value of sine 60. Sine 60 is 0.87. So I can erase this entire thing because sine 60, 0.87. Let's cross multiply now. Doesn't matter which diagonal first, I'm just going to do this one, I'm going to choose one. 3 by sine A is just 3 multiplied by sine A. And 0.87 by 4, 0.87 multiplied by 4 is 3.48. Alright? So, let us solve for A. Right? So, we are going to solve for A. Right? 3 is a multiply. Throw it across, you will get a divide. So, you get sine A is equal to, well, 3.48 divided by 3 is 1.16. But remember, we are trying to solve for A. So throw across sine, and the opposite of sine is sine inverse 0.16. Alright? Just 1 second. Huh? Right. So I need to get a space somewhere here. So type this on the calculator. You need to see this for yourself. Sine inverse, try it. Second function sine. I know why the second function. Second function sine 1.16. Type it in and press equal. Tell me what you see. You will get an error on your calculator. Alright? And this brings, and of course we did everything correct now. We got an error on our calculator. And this is a very, very, very important thing we need to discuss now. How come we did everything correct and we got an error on your calculator? Alright, so this brings us to a topic called critical angle. And anytime your refractive index is less than 1, well, I know the refractive index from air to water was 4 and 3. But the real refractive index needed from this question was from water to air, which was 3/4, or better known as 0.75. Anytime your refractive index is less than 1, there's always a chance you will get an error on your calculator. It doesn't happen when it's more than 1, only when the refractive index is less than 1. Right? So, we are going to discuss in detail now critical angle and why sometimes we get an error on the calculator, and then we'll come back to this question, right, and you will realize why this caused an error. Alright, so let me just set up the board, give me a few seconds. Alright, so let's analyze question 4 a little more in detail and where that error came from. Alright, so this was the basic scenario. The light was coming from water and it was going into the air, so it was going this way. Right, now you're going to have to do a lot of your calculations on your own here, right? I'm going to take it from this point. You can cross multiply, so you'll need to pause the video and do the calculations and then match it up with my answer. Alright, so remember the refractive index from water to air is 0.75 or 3/4. It was less than 1. And that this is the formula that you actually need to use. Water, the first letter goes on top as usual, the second letter goes underneath. So let's do the calculations. The refractive index from water to air is 3/4. In the question I just showed you, the angle of the fish was 60 degrees. Coming from the fish was 60. Let's start off at that smaller angle. Let's start off at 10 degrees. So for this question, it will be sine, and the angle in water is now 10 degrees. And we are trying to find the angle in air. Work this out, find sine 10, cross multiply, and solve for A. Please pause the video and do it yourself. Alright? And this is the answer you should get. Yes, now, sine 10 divided by 10. You are supposed to get something close to 13.4 degrees. You might get a little bit more or a little bit less depending on how you round off. So the angle might look something like this. So this angle is going to be, I'm just going to call it 13 degrees, right? Although it's 13 point something. I only have limited space here, so I don't want to take up too much space. Does this answer make sense? Yes, because whenever my refractive index, the correct refractive index is less than 1, the angle is supposed to increase. It went from 10 to 13, so it did increase. Alright? You see the incoming angle, where it's called the incoming, the first one, the angle of incidence. Let's increase this a little more. Let's increase this to a bigger angle. Let's increase it to 35 degrees. So this angle is no longer 10. The angle is now 35 degrees. Obviously, if we change the angle on this side, the refractive angle has to change also. So the new angle is 35. Calculate the new A value. Let me work this out. Pause the video and work it out. That's all right. And we should get something. The angle coming out here is now close to 50 degrees. Alright, so remember the angle was 13 degrees and now it's 50 degrees. It's getting closer and closer to this boundary because the line started out like this, and then when we increased the angle, it went down, it went up to 50, and I'm pretty sure if we increase it more on this side, it might end up parallel to the boundary. So let's try something a little bit bigger now. Let's increase this angle. It's plenty here. Let's increase this angle to 45 degrees. Alright? Right, so this angle is now 45 degrees. Right, so 45 degrees. Let's do the calculations now for the new A value. Alright, sine 45. And we get something like this. 70 degrees. Well, 70.5 is 71. Some people might get 71. Eventually, we are going to increase this angle so much. If we increase it enough, the line is going to be parallel to the boundary. So it will be on the air-water boundary. But if we increase it any more, it will have to go below the boundary, which means the light starts off in water and doesn't end up in air. It will start off in water and end up below the air, which is still water. So, and that is what causes the error. Apparently, when the angle is too large on this side, it causes the light not to enter the other medium. It causes it to be, well, the actual term is totally internally reflected back into the original medium. And the angle that causes this to be 90 degrees, so you notice this is already 90 degrees. It went from 13 to 50 to 71. If it's parallel to the boundary, that means it's exactly 90 degrees. And the angle that causes it to be 90 degrees is something called your critical angle. And anytime your angle is bigger than the critical angle, it will cause an error on your calculator. So, what is the critical angle? Well, if you go in different textbooks, you'll see slightly different formulas. But this is the one where I use. C, which stands for your critical angle, is sine inverse of the refractive index. But this refractive index has to be less than 1. Right? So, in other words, it has to be going from the more dense medium to the less dense, from water to air. Right? A critical angle can only happen if the refractive index is less than 1. Right? If the refractive index is more than 1, you cannot have a critical angle. So let's calculate the critical angle for this particular scenario. The critical angle in degrees is sine inverse. And what's the refractive index for this scenario? 0.75. And we make sure it's less than 1. Let's calculate that. Second function, sine 0.75. And that angle is roughly 48.59 degrees. Approximately, let's call it 49 degrees. Which means whenever the angle on this side is more than 49 degrees, expect an error on your calculator. And remember the one with the fish? The angle on this side was actually 60 degrees, more than 49. So that is why we got an error. So what happens when we cross the critical angle? Whenever you cross the critical angle, the boundary acts as a mirror. So that means the one with the fish, remember, the fish was at how much? This was the dashed line here. Remember, for the fish, it was 60 degrees, and it had the gentleman here, right? Looking at the fish. Let me draw it back quickly here. Right. So, he was trying to look at the fish. But remember, the critical angle is 49 degrees. So, when it crosses 49 degrees, it no longer escapes into the air. Over here acts as a mirror. And a mirror acts like this. If the incoming angle is 60 degrees, it will bounce back at exactly 60. So that means if here was 50 degrees, because 50 degrees was more than 49, it would have bounced back exactly at 50 degrees. You would have got total internal reflection. And make a note, it can only happen when the correct refractive index is less than 1. Okay? Right? So, in other words, the gentleman here would have not seen the light because the light did not make it out from water to air. Instead, it remained in the water. Alright, so this is my advice. Anytime you are given a question that has a refractive index and the refractive index is less than 1, you go ahead and calculate the critical angle, even if the examiner didn't tell you to calculate it. Calculate it, and once you get the value of the critical angle, make sure the incoming angle, the angle of incidence, does not cross the critical angle. Because if it crosses the critical angle and you waste your time cross multiplying to try to find the refracted ray only to end up with an error on your calculator, you would have wasted time in the exam. So do the critical angle check first. Alright? Alright. Next question coming up. Alright. So we'll come back to question 5. Here's a more of a past paper style question. Right? It may have some new stuff in it that you never saw before. I'll try my best to explain it. So here we have a blue ray of light trying to go from air to water. The angle in the air is 60 degrees, well, the angle in the water is unknown. Obviously, the light will be traveling at a certain velocity. Now, in case you didn't know, light has different colors of light and electromagnetic radiation. All have different frequencies, and they have different wavelengths. So when it comes to waves, here's a formula, very popular formula, to calculate the velocity of a wave. Even if it's a light wave, velocity is equal to the frequency of the wave multiplied by the wavelength. The velocity of the wave should be in meters per second. The wavelength, this funny looking symbol, should be in meters and frequency is measured in hertz. Now here's the thing. Whenever a wave is moving from one substance into another substance, from one medium into a next medium, like from air to water, the velocity can be expected to change. The wavelength can be expected to change. The only thing that remains the same is the frequency. So these two guys can change. So I'll put a little C here to remind you that it can change. But when it's going from one substance to the next substance, the frequency will remain the same. So I'll put a little S here. Alright? So that's going to be very useful in this question. And so far we haven't really used the other this formula. So let's get it. So the examiner has given us some information. The refractive index from air to water is 1.2. You notice the light is going from air to water. So this is not a trick. The velocity in air is this amount of meters per second. Note, multiply by 10 to the power 8. And the wavelength in the air is this amount of meters. Note the little n here. That's nanometers. Now when we're doing the calculations today, you're going to have to do some for me, guys. And this video assumes that you watched the basics, physics basics part 1, part 2, and part 3. So I'm just going to put down the general idea of how to do the working, and you will have to complete it from that point. So let's see. Let's find the velocity in water. So it's moving from air to water. Let's use this formula here. A-N W, the refractive index from air to water, instead of B it's W, from air to water, is the velocity, the A goes on top, is the velocity in air divided by what? The second letter goes underneath, the velocity in water. So let's plug in the values we have here. ANW is 1.2. The velocity in air, the examiner was nice enough to give us. Try this a little better. 0.98 multiplied by 10 to the power 8. Remember I showed you in the previous videos how to type in multiply by 10 to the power 8. And we're trying to find the velocity in water. So 1.2 is the same thing as 1.2 divided by 1. Your job from this point is just to cross multiply and solve for the velocity in water. So like I said, I'm not going to go through the details of this. You're just going to get my answer. Alright, so it will be 2.98 exp 8 divided by 1.2. And if you got something close to this, oh, it's a big answer. Right, I'm going to put my answer in standard form. You will actually get, no, I won't put it in standard form. The answer for this one will be 2, 4, 8. And how much trees? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 meters per second. Alright? So this is the velocity in meters per second in the water. Alright? So if you got something looking like this, you did it correct. If you were to put this in standard form and round it off, it would be 2.48 multiplied by 10 to the power 8. That's if you ignore all the trees, right? So this would be correct, or this would be correct. Alright, so we got the angle in, the velocity in water using this formula, which is real similar to this formula, except it doesn't have the signs, but you still had to cross multiply. So we figured out part A. Let's find part B. Alright, that should be easy too. Let's see. Alright, we're going to use the first formula. ANW is sine of the angle in A divided by sine of the angle in water. This one should be super easy for you guys. ANW is how much? 1.2. The angle in air is 60 degrees. And we're trying to find the angle in water. Cross multiply as usual and solve for W. Let's see what you get here. Alright, so you get sine 60 divided by 1.2. You'll get something close to 46 degrees. So this here should be close to 46. If you get 45.8 or 46.1, anything close to 46 degrees, because everybody's going to round off a little bit differently. But make sure you get that answer. Alright, the next question is, they want to know two things here. The frequency of the wave in A and the frequency of the wave in B. Well, let's calculate the frequency in A. And remember, the frequency over here in the air should be the same as in the water. So really, they're trying to trick us. We just need to find the frequency in either the air or the water, and frequency remains the same for both. Right? So the frequency here and here is the same. How do you calculate frequency? You take the velocity and divide it by the wavelength. Right? So let's start calculating there. Frequency in the air, let's do it for the air. The frequency in the air is the velocity in the air divided by the wavelength in the air. Right? And we have those values, velocity in the air and wavelength in the air. So we have 2.98 multiplied by 10 to the power 8 divided by 560, and the common n is nano, which means multiply by 10 to the power minus 9. Right? Hope we didn't fall for any tricks there. So let's work this out. I think we're going to get a really big number here. 2.98 exp8 divided by 560 exp minus 9. Got a really big number here. Frequency is 5.32 multiplied by, if we round it off, 10 to the power 14. I only went to 3 significant figures. And remember, the frequency in air and the frequency, well, this supposed to be W's, I made a mistake. The frequency in the air and the frequency in the water is supposed to be the same. So there's no need for me to work out the frequency in water. For me to find the frequency in water, I would have to take the velocity in water and divide it by the wavelength in water. Right? I think we have the velocity in water, and we had, no, well, we don't have the wavelength in water right now. That is what part D is asking us for. But if we were to find the wavelength in water and divide both of them, we will get the same answer, or roughly the same answer, because we're rounding off a little bit. Alright. For part D, I should have write down the answer here for this part here is 5.32 multiplied by 10 to the 14. Well, frequency is measured in something called hertz. Alright, so let's calculate the wavelength in water. To calculate the wavelength in water, we have to take the velocity in water and divide it by the frequency in water. So to calculate the wavelength in water, you take the velocity in water and divide it by the frequency in water. The velocity in water was this first one here. I'm going to use the rounded off value. 2.48 multiplied by 10 to the power 8. And the frequency in the water and the air is the same. So the frequency in the water is 5.32 multiplied by 10 to the power 14. Let's just divide that and we'll finish with this question. 2.48 exp8 divided by 5.32 exp 14. We got 0.000 3 more zeros, 0.00466 meters. Alright, so I really hope that you understood this question. It's a good idea to write back the question, try to work it back on your own. But what I really want you to take away from this, one of the main things, is that when you have a wave and it goes from one substance to the next substance, expect the velocity and wavelength to change. Just remember, Mr. Frequency remains the same. He's the stubborn one. He remains the same. Alright, so let's try another question. It's a trick question. Your job is to try to complete the diagram. So let's see what's happening here. Here we have light going from water to oil. Now the examiner has given us the refractive index in the opposite direction, from oil to water. So let's first of all get the correct refractive index. What would be the refractive index from water to oil? Water to oil, since it's the opposite direction, we need to flip it or invert it or throw it underneath a 1. So if we get that, 1 divided by 1.25 is 0.8. So the actual correct refractive index is 0.8 for this scenario. Remember a couple questions back, I told you that if your refractive index was less than 1, there was a chance you can get an error on your calculator and you should do a critical angle test. Remember how you find the critical angle? The critical angle is sine inverse of the refractive index, provided that the refractive index is less than 1. And 0.8 is less than 1. So let's calculate the critical angle for this scenario and see how it applies to the question. Second function, sine 0.8. We get around 53 degrees, well 53.13 degrees. So that means that anytime this angle, the incident angle, the angle of incidence, is greater than 53, I'm just going to call it 53 for short, right? At exactly 53, the angle over here would be exactly 90. That is if it was exactly 53. But anytime it crosses the critical angle, and in this question it did cross the critical angle, 60 degrees is bigger than this, the light no longer makes it out on the other side. Instead, this acts like a mirror and it bounces back inside here. And for a mirror, the angle of incidence is always equal to the angle of reflection. So here is also 60 degrees. So if here was 70, over here would be 70. You notice I didn't even bother to go to these formulas because I would have wasted my time and I would have gotten an error on the calculator. So we have exceeded the critical angle, and this caused what? Total internal reflection. Alright, so this is a short question.